Okay, thanks everyone for coming. So the rationale of this project is it was recognised that the surface lineaments is important as they can be the expression of basement structures and mineralisation systems, and so it's a way of actually looking for footprints. So it was decided that these limit trends can be expressed as landforms, geochemical anomalies, and they're associated with distinct landform patterns. So the aims of the project were firstly to compile, process, analyse, compare the linear features that can be seen in surface and subsurface data sets. To map out relationships between the surface-subsurface lineaments, to test relationships between basement structures and cover. And this was done in two ways. There's a range of approaches, and this was quite innovative part about this, and this is where we got Cyro on board, because I'm a sort of a basement geologist. I like looking at maps and making maps, and Carmen's a surface person. So we sort of got together, we could do the knowledge-driven manual mapping, but we needed people to do the subsurface lineaments and surface lineament generation. And that's where we got Cyro on board. So that's Nacho Gonzalez Alvarez's work. So the background of the study area, rather than just working within the irregular shape of the GP2 area, we've just expanded it to make it easier for processing. You can see, so it's the red square, which is a bit quite hard to see, which is sort of this box here. The yellow one is the actual GP2 formal area. You can see on the right that it's quite a complex area. There's lots of sediment types, regolith types. There's lots of scattered outcrop. It's variable. A lot of it probably doesn't exist, but this is sort of the old mapping. But what we have are a range of rock types. So it's actually quite a complex area. In the surface, we've got a series of landforms. This is what Bao Hong just talked about. We've got the paleochannel systems through here. We've got the strand lines running along here. We go into the basement. This is the 2 million mapping from the surveys. It's quite a lot of different geological units. As Claire showed this morning in her talk when she talked about this area, there's meta-sediments, there's meta-igneous rocks. And once you get down here, you start getting younger igneous rocks that are underformed. So it's quite a long-lived history. It's also got a lot of structures. You can see these black lines. There's shears, faults. There's that Mulgathing trough that's been mentioned in quite a few of the talks. So, and this is the breakdown. So a lot of people who've worked in the Gawler Craton will be familiar with this. These are the domains. All these blocks have got slightly different lithologies, but different histories. So when you look at the area, it's quite complex from the surface down in the basement. And we thought it was a really good opportunity to test the different approaches to looking at this data. I think you'll all be familiar with there's two approaches. The first one was what Carmen and I are most comfortable with. It's the manual lineament mapping. She looked at the surface features. I looked at the basement. And you can sort of see, we just sat there and just traced out lineaments. They were obvious. I'll just sort of go through a bit more about the data sets and that we used a bit later on. But the automated is it's quite an interesting process. I think I will admit that when this sort of came up, I thought I was going to do it all out of a job. But I see it now. It's actually a really helpful tool for understanding the geological system you're looking at. It can give you confidence about decisions you're making. It actually highlights features you may not have recognised because of your bias. So I actually think this is a very, very good tool for helping to work with these either surface or subsurface systems. But this lineament mapping approach uses raster data. It basically maps up. You can actually do whatever you want. You can process it using these line and catalyst algorithms to map out boundaries, gradients. You can change the parameters, so you can have as detailed, as simple as you want. This becomes a bit of a nightmare, which I'll show in a minute. It's one thing that's important. You need to understand what you want to do. You need to understand the scale of the project and what you want before you actually start doing stuff, because you'll go down a rabbit hole. So you need to actually play around, and you need to understand the geological system to get an idea of what you're going to get out of it. So we sort of ended up doing, Jonathan Irvine did this. He sort of generated coarse, medium and fine outputs. And so he produced a set of different sets, which I'll show in a sec, Now, if you have a look down the bottom on the left, that just gives you an idea of how some of the parameters that you use, and then on the right is where some of the values we use within these. So you can play around. It's actually a very flexible system. Oops, that's not meant to be blank. It's meant to be a very complex figure. I can't see the didn't know this. Okay, so for the surface geology, see, I've just got a single page, so that's where. So for the surface geology, she used a range of data sets, so Landsats, DEMs, etc., SRTMs. She then went through manually, and for each of those different data sets, drew the lines that fell out to try and understand what was going on, to sort of see the patterns. And then this is where she did it manually. This is what the algorithm generated, and you can sort of see it's the different follow the cross. Say this is, for an example, this is the DTM. This is the coarse generated lines, the medium, and the fine. And you can sort of see this is that dune field coming through here. It's picked these out really well in these data sets, but you can see that once you get to this point, at this scale, it's just a mess. So it's probably not the best way. The best way of doing it. You're better off with the course to try and understand it. So again, you need to understand what you want to get out of it before you start playing with it. The other thing I found quite interesting is this is the generated lineaments, all of them overlain for the coarse generated data sets for the surface, sorry. And you can see that it's a lot of short segments. There's a lot of, I guess, that's quite dense. You can see particularly through here we've got the dune fields. When you go to manually mapped, it's quite a different case. So this is all the different data sets. So the ASTAR, the Landsat, the DEM, all overlain. And you can see they're very different. But what I like with this is the one on this is essentially the, I guess, objective data using the algorithm. It's picking up the gradients. If it can't really make the connection between this point and that point, it stops. The one on the left, which is manually mapped, is that idea of the geologist is connecting lines. You're making connections, you're extending things. Probably this is suggesting maybe more, you're extending it further than you could. So that's a question for us to sort of ponder, but I think they end up producing very different data sets. The other thing I like that comes out of this is where the one on the right is really the, I guess I've used the word objective, it's just puts everything that it sees, where when you start drawing, if you see 3 lines, you might put 2 in. And I think there's that sort of unconscious bias to not filter, but show representative lines. And I think this highlights there's 2 different outcomes. One is that we tend to link lines. We sort of see 2 things, they're close, we'll just, you'll make it the same feature. But also we tend to probably filter to a degree that we don't realise. We did something similar for the subsurface. In this case, we used a series of aeromagnetic from data sets in the GCAS, different processing. For the subsurface lineaments, as Michael McMaster and I, as part of the South Australian Discovery Mapping, we were compiling this area. So we had the subsurface geology structures. So these are structure lines that we created. So there's trend lines, faults, features like that. And this is what the subsurface algorithm spat out. Now, I think this is quite interesting. In some ways, it highlights the difference between the geophysical data sets and the processing. So you can see down here with the tilt, say the medium has got a very even coverage because of the way it's processed. It's picking up everything uniformly. But when you go to the, say, the 1VD, 2VD, and even the RTP, you can see that where the NAWA is, it's a northwest Gawler. You've got this basins come in. The crustal features are obscured. They're quite broad wavelength. So it just shows, this actually shows you that these get filtered out. You can't see them, where the tilt processing actually highlights them. So in a way, I found this a very good tool to show you how the different data sets, geophysical data sets, pick out features. And you can see it down here with the 2VD particularly. You can see here in the NAWA, there's hardly anything, where down in these ones with the tilt, the AGC, you actually have reasonably good coverage, or across all of them, representative coverage. So I think that's an important outcome. So again, we have, this is the manually mapped on the left, so this is the lines that Michael and I drew. And on the right, we've got all the automatically mapped lines from the core. So this is everything from all the different geophysical data sets. And you can see that, again, we've got shorter features, except for up here. You tend to get long, these are the Gad and the dikes, they tend to be reasonably long. The Karari's got a few long features. We did this a few years ago. We found that you can actually, because you can colour code these lines, they've got orientation, length attribution that you can play around with, that if you sort of do natural breaks, the Gadnas came out as a population because they were sort of reasonably long and straight. Big structures came out as sort of the second population. They're not as long. Third one was the smaller faults. But the interesting one was that once you get down in this area of, say, plutons, you could actually, they'd come up as different colour where they pick out the circular features. So you end up with this sort of a way of doing analytics and looking at length of structures. And that was something I found quite interesting. And I think the other thing about this I made in my notes just then is, you can see through here, we've got this area here, we've drawn in a lot of faults crossing these Hilper plutons, which are really not as easy to pick out here. Geologists try and make a map where this is just generating lines with no context, no anything. So again, where this has got, say, any geological interpretation would be dependent on the geologist. This has orientation, length, feet attribution. Now, once we've done all this, what can you do with it? And something you can do, which is quite interesting, you can do density maps, say how close are they. You can sort of have orientations, length, you can start clustering. So in this case, this is I think the lines are the interpretation for the manual interpretation for the subsurface, and the basement is the manual interpretation for the surface. So you can sort of start looking for patterns. So if you want a big structure, you want to see, do you have a surface expression? Where are those relationships? So you can sort of start getting a sense, up through here where you got the Kurubi shear zone, you can see there's a hint of a pattern through there. So is that telling you something about reactivation? You can go back and look at that and just say, is there a correlation between the subsurface or the aeromagnetic interpretation versus the surface features? So you can start playing around things like that. Another part of this project, this was Thomas Albrecht at CSIRO. He did this a few years ago. And what he did was he sort of had an algorithm where you could actually pick out landforms. This is a landform recognition pattern. But if there was this landform had the same characteristic across the same data sets as the other, something nearby, say, this one here has the same characteristics as that point there. It then starts filling in the gaps, linking them and making these maps. And you can sort of see here, around the edge of this dune field, around the Ulduri Range, you can see that there's different landforms along there and down through these, the Spartan Range. You can see it's starting to pick these out. Now this can be done in two ways. One is, this is a trained version where they selected, so you looked at the area and decided there were 7 different types of features. So it could be lakes, it could be dune fields. And you sort of say, okay, find everything that looks like this. And then it just sort of then generates these types of maps. In that case, with the trained ones, you say, specify how many data sets or how many patterns you want to pick out. In the untrained version, you just basically throw it in and it'll spit out how many it finds. It could be 20, it could be 50. And that's a bit random, but often these things depends on your time, your need. That may be the way to go. I mentioned before the orientation data, and this is one of the parts of that. I actually found this quite interesting. I'm not a big fan of autocorrelation, but we sort of talked before. You can see here the Nawa's got this. This is the generated lineaments. You can see it's got this trend here parallel to the Karari shear zone. But when you come down in this area through here, these are the Gad and the dikes through here. But when you look here, there's actually a lot of detail which hasn't been generally not picked out because it's considered that bland blue zone. there's actually a lot going on. And because you can colour this based on orientation, you can start playing with it. This has got 20-degree bins, but you can go smaller. For example, this feature that wraps up through here curves gradually. You can actually do 5-degree bins and quantify that change if you wanted to. Because I think that's quite interesting, because when you look at it, this sweeps around like that. This one goes like that. So if you were to look at each of those features separately, you'd get separate kinematics. So it's sort of raising that, to me, then sets the alarms off of what's actually happening there. Is it textural? Is it sinistral? Or is it actually shortening? And you've got that sort of deflection. Down in the Neutz domain is another good spot. You can see that you've got this east-west grain, which when you look at the actual aeromag, you can see is the general layering within the rocks. But then you can see this, it's the same as the Caniba shear zone through here and the Kirby. You've got these structures that come through and offset it. So in a way, it sort of helps you quantify and observe features, but again, it's a tool, and you need to understand the geology before you can actually start to make sense of these. They're just lines with no interpretation. So you need to understand geology. So it's not doing its out of a job. So learnings and recommendations. The study has established a methodology and tested data sets to interpret and generate surface and subsurface lineaments. The report books have actually got how to do this. So if you have your own data sets, raster data sets, you can play with this, which is something we encourage you to do. There's a report book which Carmen's led, it's come out. It's got examples of some of the analysis that we've done, but I think it's one of those open slather, have a look, play, see what comes out. There's a data set that comes with package that comes with the report book, and that can be sort of looked at, played with, compared with what you do. And then just remember, it can be used to test, understand, provide confidence for geologically interpreting geospatial, geophysical data. And just one of the main things when we started this, it was looking for that link between surface, subsurface features, and just like to stress that the outputs of this study are designed to help explorers. We want people to use this, look for patterns, use as a way of understanding the surface, subsurface geology, the relationships, connections, and find more stuff. Okay, thank you.